So another process which is important in high energy particles is light, for example, very high energy light, or what we call photons or gamma rays. Actually, what happens is when it interacts with the nucleus, it produces an electron and a positron. Positron is just the antiparticle of electron, it just has a positive charge. And this is a very important process for detection and for many other, it has many other uses. So we discussed essentially synchrotron radiation, inverse Compton scattering, and pair production. There are other processes, but at the moment, let's not worry too much about it. And now, naturally, now that is a very important aspect, and I touch very briefly on this aspect, though I should be talking about a longer time, is the particle detectors, because these are not anymore your, as I told you, optical telescopes or radio telescopes. Now, particle detectors at high energies come in very different, they're actually different beasts. Now, one of the very important detectors is what we call a scintillation detector. And what a scintillator essentially is, when, for example, some particle comes and hits it, it gives out light. And you can study the little more detail. There's about this slide actually. And this is a very kind of what we call a very venerable detector in nuclear physics and particle physics in the very early days. Even today, it's used quite a lot in cosmic rays and other work. And very interestingly, very famous Rutherford experiment, where he really detected the for the idea of nucleus, used these scintillation detectors. And what it has is, I'll tell you very briefly again, is a what we call a kind of a plastic. It's like not a regular plastic, but will be kind of a doped thing. And as I said, when the particle hits it, it gives out light. And another important aspect, component of these detectors is what we call a photomultiplier. Is shown in the right part of the bottom slide there, bottom part of the right slide, bottom right, and that essentially takes a photon and it gives you a nice electronic signal. And these are actually used very, very much in the all high energy astrophysics world. And these are what we call workhorses of this thing, of these suites. And another very interesting phenomena which is used in particular in the high energy detection is what we call Cherenkov radiation. This is something which could be, which probably is not very familiar to some of you. Now, here, what happens is if a particle has its velocity more than the velocity of light, just watch carefully, not the velocity of light in the medium. See, after all, light has to pass through some medium, correct? Now, right, when it passes through, for example, water, actually its velocity decreases and it's only 0.75 c, it's not c anymore. So there could be other particles which have more velocity than this. So please don't get confused here, because no particle has higher velocity higher than light in vacuum, but in medium it could be. Okay. So when this happens, what's called Cherenkov radiation comes out. This is essentially a kind of a mostly blue light, and this is seen with air, in the water, and in many other media. And this is now a very important part of detection of high energy particle. And actually, at the very end, when we talk about our experiments, our telescopes in the Hurley, we will talk about this particular process. Now, please remember that the velocity has to be greater than c by n. N is the refractive index, which is of course a function of the wavelength. Now, the right hand side just shows a blue light. In nuclear reactors, actually, because lots of interactions are taking place, you get this blue light, which is a very common thing if you could go near a nuclear reactor. Now, it's slightly some more about Cherenkov radiation, because we will be talking about it much later. And if you work out the formula, it is kind of is proportional to 1 by lambda. Lambda is the wavelength, and so naturally what happens is the blue light dominates this type of thing. Okay, you can just think about it. That's what happens there. And this is a little more about Cherenkov radiation. What happens in particular air, water, because these are the detectors which we will be using in high energy astrophysics, both in water and air. So this is what type of energy it should have. For example, in air it should have at least 26 million electron volts. Okay, another thing which is used in some of these studies is what we call calorimeter. This is essentially gets the energy of a particle. You can see the left hand side, this is an earlier cloud chamber picture. What happens when a particle comes and hits? Now it makes more and more particles, and it comes down, and you can see enormous number of particles are produced. Please keep this in mind, because we will be talking about the same phenomena later, but the material will be air, not this is some type of a metal there. And so you can see, if you can get hold of all these particles, naturally you can measure the energy of it. This is a very big thing, and it's used in you might have heard experiments like LHC, etc. Okay, now let's get on to what exactly the three things we are going to talk about: gamma rays, cosmic rays, and neutrinos. Neutrinos only if you have time. And cosmic rays are a very fascinating field, and especially I should mention it, India has done enormous work in it for the last 50, 60 years. They were discovered early in almost a century ago by a person called Hess. What he found was he went up in a balloon, found that his detectors, those days it's called electroscopes, even though today those are used, and he found charged particles really hitting his detector. And so he called this cosmic rays. There are some lot of debate earlier whether they are photons, because that's when they thought to use the word rays there, but they're particles. As we will see later, they're actually just charged particles. And what are the important things about it? They are charged particles. That's why, for example, if you do your experiment in the poles and the equator, you will see a big effect, okay? Because the Earth's magnetic field is affecting those particles. And they are mostly protons and neutrons, atomic nuclei. That's why I told you at the very beginning itself, this is in these fields, the micro and the macro come together. Now these are all the micro aspects of the thing, okay? And so now the very important part, what I want to tell you, is actually the next slide. You just see now, just spend a little bit or a minute at this. So on the right hand side, we have a graph here, and what it shows in the y-axis is the intensity, it's the number, and this is the energy. Now this is what we call a power law. Don't worry too much about it, but you can see that the intensity comes down very fast. The very left hand corner, it's particle per square meter. Like if you put a meter detector, you will get this hit. Okay, you will get a particle per square meter. But as you go higher up in energy, it gets very, very small. And you also please consider the energy we are talking about, 10 to the power of 20. This is super energy. Because why I call it super? Because you may know what's called accelerator. That means man has been trying to accelerate particles in the lab, for example. The LHC is its latest, but it has come nowhere near that. And with all types of progresses, we are actually, human beings are stuck somewhere in the middle of the plot here, 10 to the power of 14 or 15. So the curiosity is, what type of process makes these energies, these particles with high energies? What is the astronomical source, astrophysical source? So this is where cosmic ray becomes a part of our high energy astrophysics. The question here is, where are such high energy accelerators? Do we have them? But we should have them, because obviously we are getting such particles.